Have you ever wondered where the formula for the circle area or the sphere volume come from? Or even what lies beyond in 4, 5 or even 6 dimensions? Normally, we need to use calculus and a bunch of integrals to get these answers. But in this video, I'll show how you could arrive at the right answer reasoning only in terms of probabilities. The idea for this video came from a problem posted in Discord for the Summer of Mathematical Exposition community. And you should totally check it out if you're a math lover. Link in the description. I'm going to start with a step-by-step solution of this problem and then slowly generalize the reasoning, which in the end will get us the volumes of hyperspheres in any dimension as well as the volumes of some more exotic shapes. To understand the question, we need some concepts from probability. The first one is the idea of a random variable. We can roughly think of probability as a subject that studies experiments whose results are not initially known, like throwing a coin or rolling dice. Any number that we can obtain from these experiments, like the sum of 3 dice, is called a random variable. Related to the concept of a random variable is the idea of a cumulative distribution. Even though we don't know beforehand the results of an experiment, we still know how likely the different outcomes are. What a cumulative distribution is just a function f of x given the probability that x is less than a. So if x is the result of a dice roll, its cumulative distribution looks like this, with the function increasing by 1/6 at each of the possible outcomes. What will be important in our problem is that two variables with the same cumulative distribution are equivalent, even if they originate from completely different experiments. Lastly, we must clear up what's meant by random point or uniformly. Basically, this means that we are picking points with no bias. The way this is done is that if we are picking points in a one-dimensional region, the probability that the picked point is in a given subset is proportional to its length. For two-dimensional regions, the probability becomes proportional to the area, and for 3 dimensions, it's proportional to the volume, and so on for higher dimensions. For example, if we draw a point uniformly in a square, the probability that the point is inside of a given circle is proportional to the circle area. Since the probability of being inside the square must be 100%, this leads to the probability being the ratio of the areas. We can now tackle the first 2 items of the problem. In the first item, we're drawing from a circle of radius 1, and we want the probability that x squared plus y squared is less than c. Since we draw uniformly, this is the ratio of the areas of the 2 regions. X squared plus y squared less than c corresponds to a circle with radius square root of c, while x squared plus y squared less than 1 is a circle with radius 1. Putting everything together, we get that the probability is c. An interesting point that will be important later is that this is the cumulative distribution of x squared plus y squared. For the second item, note that choosing 2 points, x and y, in the interval 0, 1 is equivalent to choosing a point, xy, in the square with side 0, 1. The only difference is that we're choosing each coordinate separately. We want to know the probability that x plus y is less than 1. This is equivalent to the region below the line y equals 1 minus x, which is this triangle. It has base 1 and height 1. So its area is 1/2, and since the square has area 1, this leads to a probability of 1/2. The final item requires a bit of a leap. Suppose we have a number a, drawn from the interval 0, 1, and a point xy, drawn from the unit circle. The cumulative distribution of a is the probability that a is less than c, which is the probability of a being in the interval 0, c. Since this interval has length c and the interval 0, 1 has length 1, then the probability must be c. But if we recall, that means x squared plus y squared has the same cumulative distribution, and so we can interchange a and x squared plus y squared. But how can we use this equivalence to find the volume of a hypersphere? We can start by considering the set minus 1, 1 to the fourth power. This is a hypercube, which can be seen by looking at its lower dimensional cousins. As with all cube-like things, we get its volume by multiplying the sides. The first reason we are looking at the hypercube is that the hypersphere fits inside. This can be checked algebraically, but it's just a continuation of a pattern in lower dimensions. The unit circle fits the unit square, and the unit sphere fits the unit cube. This is important because if we consider a random point in the hypercube, we can write the volume in terms of a probability. However, with an argument similar to what we used for the second item, drawing from a hypercube is like drawing in two squares independently. And each of the chosen points will be inside the respective unit circles with probability pi over 4. If either point is outside of their circle, then either x squared plus y squared is larger than 1, or z squared plus w squared is larger than 1, leading to the point being outside of the hypersphere. On the other hand, if they are both inside, then x squared plus y squared and z squared plus w squared are both uniform. So the last hurdle for the point to be inside is that these two uniform variables add up to less than 1. But that's exactly the problem we solved in the second item. This happens with probability 1/2. So the journey we took is that we drew a point in the hypercube, interpreted this as drawing in two squares, checked if each of these points was in their respective unit circle, which happens with probability pi over 4 each. We then reinterpreted this sum of two squares as uniform variables, and finally, if these two uniforms add up to less than 1, then that means that our original point was inside the hypersphere all along. So we have a final test with probability 1/2 to be cleared. Multiplying the probabilities leads to pi squared divided by 32, and using our earlier relation, a volume of pi squared divided by 2. This is the case for radius 1. For a general radius r, we can use the scaling law. If an object has one dimension and it's scaled up by a factor f, then the length is scaled by the same factor. For 2 dimensions, the area scales with f squared, and so on. For d dimensions, the factor is f to the power of d. So since our hypersphere has 4 dimensions, the more general formula for the volume is pi squared times r to the 4th power divided by 2. As far as the original problem is concerned, we're done. However, it's possible to extend this reasoning to higher dimensions. Suppose that instead of 4, we're considering a sphere with a higher but even number of dimensions. Just like in 4 dimensions, we consider the corresponding unit hypercube, minus 1, 1 to the power of 2n. And following the pattern for smaller dimensions, the volume of this hypercube is 4 to the power of n. From here the idea is very similar to what happened in 4 dimensions. Drawing from a hypercube in 2n dimensions is equivalent to drawing points in n squares. Each of these points is inside of its corresponding unit circle with a probability pi over 4. This leads us to n uniform variables, and the original point was inside the hypersphere all along if and only if the n uniforms add up to less than 1. If the probability for this to happen is Pn, then we have that V divided by 4 to the power of n, which is the probability to be inside of the hypersphere, is pi over 4 to the power of n times Pn. And rearranging, we see that the volume is just pi to the power of n times Pn. This still leaves us with the question of how much is Pn. Looking at n equals 2 and n equals 3, we see that x plus y less than 1 defines a triangle, while x plus y plus z less than 1 defines a pyramid. Note that the area of a triangle is the length of the base times the height divided by 2. The volume of a pyramid, on the other hand, is the area of the base times the height divided by 3. In general, the volume of an n-dimensional hyperpyramid is the volume of its n-1 dimensional base times the height divided by n. The region we want the volume to find the probability Pn will be a hyperpyramid, and it has a special property that the base will also be a hyperpyramid, which will also be true for the base of the base, and so on and so forth. We can see this if, for example, we look at x plus y plus z less than 1. The base is x plus y less than 1. This happens because we are at the region z equals 0. For the same reason, the base of x plus y plus z plus w less than 1 will be x plus y plus z less than 1, because we are at w equals 0. So the volume in n dimensions is 1 over n times the volume in n-1 dimensions, which is 1 divided by n-1 times the one in n-2 dimensions, and so on and so forth, leading to Pn equals 1 divided by n factorial. Putting everything together, the volume of the unit hypersphere is pi to the power of n divided by n factorial, and for a general radius, this leads to pi r squared to the power of n divided by n factorial. Another direction we can extend these ideas to is to look beyond spheres. Up until now, we consider spheres, that is, regions described by a sum of squares of variables, like x squared plus y squared plus z squared less than r squared. An equivalent way to write this equation is to use absolute values. Now, suppose that we change the exponents while still keeping them all equal. If we do this, we end up getting regions like this square-circle hybrid for exponent 3, or this star for exponent 1/2. In general, these objects are known as LP balls, and their general equation in n dimensions and radius r is this. In order to get some intuition about these new objects we're dealing with, let's look at some examples in 3 dimensions. Like in the 2-dimensional case, the case p equals 1/2 is star-shaped. And this is actually the case for all the values of p between 0 and 1. For p equals 1, we get an octaedron, and as p increases, we get closer and closer to a cube, but still maintaining rounded edges. Here's how you can get the volume of some LP balls. The radius r of a ball is still a scale factor, just like with regular spheres. So consider the case p equals 3 in 3 dimensions. Using just the scaling law, we can find this ratio of volumes. However, if we were to draw a point from the unit ball, this would mean that the probability that the sum of the cubes of the absolute values of x, y, and z is less than c would be c. In other words, this sum of 3 cubes is uniform in the interval 0, 1, just like the sums of 2 squares when we were dealing with spheres. Once we know this, we can repeat pretty much the same argument done for spheres. Drawing a point from a hypercube in 3n dimensions is the same as drawing points in n independent cubes. Each of these points will be inside the corresponding 3-dimensional ball with probability V3 divided by 8, where V3 is the volume of the 3-dimensional ball. Each of these points will lead to a uniform variable given by the sum of the absolute value of the cubes of their coordinates. And the original point would be inside of the 3n dimensional ball if and only if the n uniforms add up to less than 1. which happens with probability 1 over n factorial. Putting all together, this would lead us to a volume of v3 to the power of n divided by n factorial for the free n-dimensional ball. To look at other values of p, it's useful to define a more consistent notation. I'll call v of p and d the volume of the LP ball in d dimensions and radius 1, while vpd of r will be the case with radius r. So what we just found is that v3 is the nth power of v3 divided by n factorial. If p is a positive integer, I can use the same reasoning to find that this sum is uniform. From there, we'd get to v of ppn equals the nth power of vpp divided by n factorial by just replicating the reasoning we did for spheres. Finally, using scaling, we get this general formula for an arbitrary radius r. But what if we wanted to go even further? You see, for L1 balls, this reasoning covers all dimensions. In particular, since v11 is just the length of the interval minus 1, 1, we can get this nice formula. But for L2 balls, that is, spheres, the formula that we found only covers even dimension. For L3 balls, the formula covers only dimensions 3, 6, 9, etc. Another problem is that we just can't tackle the case where p is not an integer. This leads to something very instructive. You see, a major way math advances and we discover new things is in trying to find patterns, and once a pattern is found, trying to prove the pattern is correct. The relation we found with our reasoning so far is this one. And what's preventing us from talking about any dimension we want is that n needs to be an integer. But what if that wasn't the case? We could maybe try extending the factorial in the denominator to non-integer values. Gladly, there's a function that does just that, called the gamma function. I linked a really good introduction video about it in the description, but the gist is that gamma of n plus 1 equals n factorial when n is a positive integer. However, gamma extends beyond the integers, while still satisfying this relation, which is very reminiscent of how the factorial works. Its actual definition is this integral, but that won't be important for now. What's important is that we can make a guess that what is actually happening is that this is the volume. This type of guess is what we call an ansatz. The idea being that we can start by exploring the consequences of this guess and later try to prove it. The first thing is that for n equals 1 over p and r equals 1, this guess would lead to this expression for v of pp. But vp1 is the length of the interval minus 1, 1 when p is larger than 0, because in this case the absolute value of x to the power of p being less than 1 is just the same as the absolute value of x being less than 1. Since this means that vp1 is 2, we can substitute this in our guess and get this expression for vpp, where in principle we can calculate everything. So if we now consider n equals d divided by p, we will end up with an expression for vpd of r that is derived entirely from our ansatz and depends only on vpp. Substituting our previous expression for vpp, this leads to a full-blown formula for the volume of an LP ball. Let's test this in a case where we know the answer, the three-dimensional sphere. V23 should be the volume of a regular sphere with radius 1, that is, 4 pi divided by 3. Our expression says it is the third power of 2 times gamma of 3 halves divided by gamma of 5 halves. However, since gamma of z plus 1 equals z times gamma of z, then gamma of 5 halves turns out to be 3/4 of gamma of 1 half, using the property twice. Using the same property, 2 times gamma of 3 halves must be gamma of 1 half, so the volume is 4/3 of the square of gamma of 1 half. So if this expression is correct, we need gamma of 1 half to be the square root of pi. We can check this in a calculator, and indeed, this is the case. Another thing that our ansatz allows us to do is to consider non-integer values of p. For example, if p equals 1/2, then we'll get this volume where we first substitute just p equals 1/2. Then we use the connection between the gamma function and the factorial to get this expression 4 to the power of d times r to the power of d divided by the factorial of 2d. So if we are correct, the volume of the three-dimensional star from earlier would be 4 times r to the third power divided by 45. This is all very nice, but how can we actually prove that the ansatz is correct? First, note that if we are in one dimension and p is larger than 0, then Vp1 of r is just the length of the interval minus r, which is 2r, matching our formula. So we are correct for one dimension. We can then use a technique called induction. We suppose the formula is valid for some dimension d, and we show that this implies it must be valid in dimension d plus 1. It becomes then just like dominoes. If it works for one dimension, it must work for 2, then 3, 4, and so on. We'll need to use some calculus for this. We start with the expression for Vpd of r, which we are going to assume is correct for d dimensions. To find the volume of an LP ball in d plus 1 dimensions, we will need to integrate the volume of a d-dimensional section. Looking at the section at some height c, we see that it is also an LP ball, but with a different radius r'. Since we are assuming that the ansatz is correct for d-dimensional balls, then the volume of the section would be given by this, and integrating over c from minus r to r would give us the volume of the LP ball in d plus 1 dimensions. To do this integral, we first note that the function that we are integrating is even in x, so we can use symmetry to simplify it a bit. Once we do that, we pull out of the integral all of the parts that have nothing to do with x. Next, we note that the thing that is out of the integral now is just 2 times the volume of an LP ball in d dimensions, that is, 2 times Vpd of r. Focusing now just on the integral, we can do this variable change and then pull out some more constants out of the integral. And the trick is that this integral can be solved in terms of the beta function. This function is defined in terms of this integral, but the important point for us is that the beta function is related to the gamma function by this relation. Beta of AB equals gamma of A times gamma of B divided by gamma of A plus B. A place where this relation is shown is linked in the description. What this means is that Vp of d plus 1 of r can be written as a factor depending on the beta function times Vpd of r. Expanding the beta function leaves everything in terms of gamma, and finally, we can use a property of the gamma function. Since we are assuming that our ansatz is correct in d dimensions, we can substitute it in Vpd of r. Once we do this, things cancel out, and all that is left once we reorganize is the expression for our ansatz in d plus 1 dimensions. What this means is that the ansatz in d dimensions implies that it is correct in d plus 1 dimensions. Since we already know that it is correct in 1 dimension, it must also be correct in 2 dimensions, 3 dimensions, 4, 5, 6, and so on. Taking a step back, what I did in this video reflects the way that math evolves a lot of the time. First, I started with well-grounded facts. In our case, the roots are handling probabilities. I used these to get the volume of an LP ball when the number of dimensions is a multiple of p, and I noticed there was a pattern. I then made a conjecture that if I used the gamma function, I could extend the pattern. This led me to a formula for the volume of an LP ball in any number of dimensions. But at this point, this formula is nothing more than a guess. We need to either prove it or show that it is wrong and throw it out. At this point, I showed how to use calculus to finish the proof, which, while it still involves integrals, they're much simpler than the usual root, as long as you're aware of the beta function, of course. If you want more math, why not check this video about visualizing complex functions? I hear it's pretty cool.